Rate and state friction experiments are illustrated here. And you have a core with a fault, and the experiment is such that you're going to slide the fault block across the fault surface at two velocities. So you start out at the lower velocity V0, which is shown here, and you measure the coefficient of friction, it's mu naught. Then at some point, you raise the velocity and you're sliding at a faster velocity. So you raise the velocity instantaneously and you maintain the new velocity V till the end of the experiment. And what you observe with regards to the change in the coefficient of friction is shown at the top. So mu naught is the coefficient of sliding friction at V naught. Then at that instance, when you raise the velocity of sliding, well, mu naught instantaneously jumps to a value I'm going to call mu star right here. And that jump is referred to as a direct effect, and it's A. So this interval is A. Is mu star minus mu naught. It's your direct effect. It's the difference between the original coefficient of friction and the instantaneously high value of coefficient of sliding friction. Then, like I said, you're going to keep the velocity constant, right? And when you keep the velocity constant, what you actually observe is that the coefficient of sliding friction drops gradually to a new value, which is mu. So that drop from that peak to the new value, mu, which is mu star minus mu naught, that's what the drop is called B, is the evolution effect. So you have the direct effect, which is mu star minus mu naught, and you have the evolution effect, mu star minus mu. And so we can calculate A minus B, right? Because A is the direct effect, B is the evolutionary effect. And A minus B is this interval right here, which in this case is greater than 0. So if A minus B is greater than 0, the fault is said to be stable. It's also said to be a stick slip. No, it's the other one which is stick slip. It's also said to be a creep fault. It's also a velocity, this whole experiment is called velocity strengthening in this case. Why? Because it appears that the strength of the rock increases. Why do we say the strength increases? Well, these mu's are the slopes, right, on the Mohr circle. When you're drawing the Mohr line, right, when this is tau against effective normal stress. If the slope is bigger, then the circle you can draw under it is bigger. If the slope is smaller, the circle you can draw under it is smaller, and the circle gives the maximum allowable stress state. So smaller circles corresponding to small slopes means the rock is weaker. So here mu increases, so bigger circles, the rock appears to be higher due to increase in velocity, which is why it's called velocity strengthening. In the second case, it's called velocity weakening. Why? Because the mu naught, mu used to be mu naught, right? After the experiment, it settles to a lower value of mu, so smaller circle velocity weakening. Another name for this is stick slip fault. And obviously, it's the unstable fault, which can actually produce earthquakes because you continue to have more slip across other faults. It can cascade and lead to several earthquakes. And what's the difference? Here you start out same experiment, right? Just a different rock. Typically, the nature of the fault is different. It could be, or even the constitution of the core is different, right? Typically, it's the one with more or less clay content that defines these different behaviors. We're going to see that on the next slide. So we start the experiment with mu naught. Observe the direct effect when we jump to a higher velocity, and the velocity drops, right, at a constant higher value of velocity, but it drops to a smaller value, right? So mu at the end of the experiment is actually less than mu naught, meaning a minus b is now less than 0. Previously it was greater than 0. Now it's less than 0, and it's because the b was bigger than the a, right? And like I said, this tends to produce earthquakes. And this is all that's discussed here. If you raise the rate at which the fault is sliding, which is what we're doing in the rate and state friction experiment, the mu will increase instantaneously, then slowly evolves to a value which could be higher or lower than the original mu naught at the lower velocity. Some faults move suddenly and produce earthquakes like these, the unstable faults, and some move slowly and creep like this, which is why it's called creep faults. In velocity strengthening, like I explained, a minus b greater than 0, also called creeping faults, the faults appear stronger or more stable as it tries to slide at a faster velocity, meaning you're going from v0 to v. In velocity weakening, the second case, also known as stick slip fault, the fault appears weaker or unstable as it tries to slide at a faster velocity. And the main thing is whether it appears weaker or stronger when you slide it at a faster velocity v. And these are the results for the different unconventional rock samples that we had looked at before, the dark and the light shale samples. It turns out that the light shale samples tend to exhibit the unstable fault, velocity weakening, and the dark ones tend to exhibit velocity strengthening. And how do we know this? Because we're plotting a minus b right here. A minus b less than 0, what do you have? Velocity weakening. So this is velocity weakening. It got weaker at higher velocities. And this is velocity strengthening. Which one could produce earthquakes? This. Right? Because the system becomes unstable and you continue to produce more and more earthquakes. Another observation is that the coefficient of internal friction actually decreases as the clay content increases. And we already talked about this previously, that the dark samples are the ones that have higher clay and organic content, which is why they plot to the right. So you see mu is decreasing from a value of 0.8 systematically to a value of about 0.4. And that's what we summarize here, that the coefficient of friction for a fault decreases as clay content increases. Clay content increasing, coefficient of friction decreasing. So the fault gets weaker as their clay content increase. How do we know they get weaker? That's what I'd explained. If you plot tau shear stress against effective normal stress, 0.8 could be here, and 0.4, which is what this is 0.8, this is 0.4. 0.4 could be half of that, right? And what's the maximum circle you can draw, say, touching about this point? For the first one, you can draw, let me use the same color. At 0.8, you can draw a circle this big, which can't even show up completely. And for the second one, you can draw a small circle, much smaller, right? Just because of the slope. This is 0.4, and the other is 0.8. And the smaller circle specifies the maximum allowable stress state, right? Which is precisely this stress. For the small one, for the 0.8 slope, you can't even see it on this slide. It's to the right of this slide, and that will basically mean a stronger rock. So smaller slope, weaker rock, and smaller slope comes from the coefficient, the value of the coefficient of friction, right? So faults get weaker as their clay content increase because the coefficient of friction gets smaller as the clay content increases. At higher sliding velocities, faults with high clay content tend to become more stable and creep. How do we know this? From the value of A minus B. A minus B greater than 0, and that's the stable or sliding creep faults. Whereas those with low clay content exhibit velocity weakening, as evidenced by their negative value of A minus B.